this computer. And I'm screen sharing, but I don't see that I'm recording. So let's try that again.
It says recording on my machine.
Oh, okay, good. I just don't see it on mine. All right. So we've went through, we're now in lecture 12. So I thought one of the things I would do this week is review from the beginning what we've been going about. Because by this time, we've probably almost forgotten what the hell we've done before. So I'm going to try it for hopefully a quick review. All right, we don't have to go through the abstract. I do want to do the review. We're going to do coding and and code systems, in particular Hamming distance, and I meant Hamming codes in the first one. I make so many damn errors. Okay, I always spend an extra half an hour to an hour at the end going back and changing all the typos and stuff in my code. All right, so like I said, I don't think we need to talk about that. We're now on chapter 12. I was putting together this image when I realized that we had studied a lot of material, so I thought maybe it would be a good thing to review it. And we also had a new participant, so I thought I'd review the material, etc., but he hasn't joined up today. All right, we started with thermodynamics, the empiricism version. We talked about prominent physicists such as Robert Boyle and Boyle's law, Jacques Charles and Charles' law, Lorenzo Avogadro's law and number, and all of these things provide the basis for the empirical equation of state or ideal gas law. We talked a lot about different kinds of equations of state, but we've primarily focused on the ideal gas law. So thermodynamics defines something called state variables, which are generally completely independent of the geometry of the object under study. So there's only, for instance, in a gas, there's only pressure, volume, and temperature. All of those things, whether you do it in a sphere, a peanut, a cylinder, a cube, you name it, doesn't matter what the geometry is, you get the same results. So the initial empirical laws, Boyle's law, was the pressure times the volume is a constant, provided that the temperature is held constant. Charles' law said that volume divided by temperature is the same as a constant, provided the pressure is held constant. Avogadro's number, Avogadro's law is the volume is proportional to the number of moles. And a mole is a fixed number of molecules of gas, and N sub A is the usual notation for Avogadro's number, roughly 10 to the 25 or 26, whatever the number is, giving you the number of molecules of the gas in a mole of the gas. And this is, of course, holding the pressure constant and the temperature constant. So we found that physicists can be confounded about physical systems, but they had often thought that heat was a fluid, and it took a while, but they eventually figured out that it wasn't a fluid. It was actually energy. The first law of thermodynamics is conservation of energy, something that is very important in physics. And we took some care understanding that energy is internal energy, heat, and mechanical energy, W. So energy is a state variable, but Q and W, the components of it, are not state variables, which is a little non-intuitive, but it's because energy is conserved. The sum of the two is conserved, but the individual ones do not have to be. You can change one into the other and vice versa. So for a non-state variable, the process is path independent. That is, the way in which you perform the action of the process will get different results. So we showed that there were various forms for specific heat, but in the ideal gas law, there's simply a constant times temperature. And there are important processes that follow. The first law of thermodynamics, as I said, is conservation of energy. And the important processes that you need to think about are isothermal, that is constant temperature processes, isobaric, constant pressure, adiabatic, no heat added. So all of the change in the energy will only be due to mechanical work. Cyclic systems, beginning and end positions are the same. Two isolated, that is, not able to exchange any energy or mass with their environment. That's what isolation means. Two isolated interacting systems will only exchange heat. And we discussed calorimetry, the measurement of heat capacity, the mole specific heat using a constant alpha for each gas, the area under a path in the PV plane measures the mechanical work. So a path can be saying what is happening in the PV plane, and that the area under that measures the mechanical work. Okay, there are very important processes. Free expansion of a piston causes no change in the temperature. The mechanical work of an isothermal process for an ideal gas law is a constant times the log of the final volume divided by the initial volume. The path of an adiabatic process in the ideal gas follows PV to the gamma equals a constant. where gamma is a function of the alpha, the in the particular gas. Okay, for all gases, we're going to discuss with alphas on the order of 1. For example, helium, alpha is 3/2, or nitrogen, alpha is 5/2. These are approximately 1 numbers. So I went on to the properties of the ideal gas law in thermodynamics. Generally, we will talk about pressure, volume, temperature, energy, and entropy, and the state functions. Now, most of the state functions, such as the ideal gas law, are essentially energy conservation. Pressure times volume is an energy. Pressure is force per unit area. Volume is distance times area. The area cancels, so you have force times distance, which is energy. And the constant times temperature is also energy. So the ideal gas law is just a statement of energy conservation. Entropy is also a state function, but a little bit more abstract, but obviously quite useful. So we moved on to reversible and irreversible path, that is, irreversible systems were those that were path dependent. Reversible were ones where they were path independent. Isolated systems, isothermal systems, constant energy systems, adiabatic systems, all of these things. Reversible and irreversible state changes, the way in which these processes work. Entropy and the second law of thermodynamics. We were talking here in the old mechanical thought about it. We moved on to the beginnings of statistical mechanics, and primarily Maxwell. In particular, the shift was from all of these mechanical measurements to an understanding of how the probability of the various interactions in the gases reacted. So we did a short history of modern probability, Kolmogorov's axioms, monotonicity, the complement rule, numerical bounds, the sum rule. By the way, please, at any time when any of this looks like and you say, what the hell is he talking about? Please stop me and explain or ask so that I can. One of the things that always drives me crazy is when I ask at the end, did everybody follow? And people say, oh, I got 15% or whatever. And it's like, I'm sorry, I keep asking, please ask questions. I want you to at least get 90% of what's going on. So the sum rule, the difference between God's probabilities, frequentist, versus Bayesian probabilities, observer dependent. Events and probabilities of events, which are not the same thing. Random variates and their domain, and probability distributions. We also reviewed joint probability distributions, marginal distributions, which are integrations over joint probability distributions, conditional distributions, which are expansions of joint probability distributions, or at least one of the components in it. If you have a joint probability distribution on two variables, you can integrate it and get the marginal distribution, and then the joint probability distribution divided by the marginal distribution is the conditional distribution. And obviously it's also symmetric. So if you have y given x, you can calculate x given y. They're both just based on the joint probability distribution. The product rule, which is the joint is the product of the marginal times the conditional. Bayes' rule on how to update your prior probabilities to posterior probabilities. We did an example with the Monty Hall problem that is very hard to understand, but the truth is every time that Monty asks you to whether you should change from your choice to another one, the answer always is yes. Bayesian learning, we showed how if you were very ignorant about how a thumbtack would show the probability of a thumbtack showing face up, you could do a whole bunch of experiments, and using Bayes' rule, you can start your very ignorant prior and keep getting, with each new toss of thumbtack, you get a new posterior. And we showed that as the number of thumbtacks went to infinity, the narrowness of your posterior kept getting smaller and smaller and smaller. So prior distributions, the ones we were talking about, are observer experience, and experience includes all actual measurements that have been done. And then posterior distributions are obtained from the joint probabilities using Bayes' rule. So in order to understand the concept of phase space and entropy, we did probably one or two lectures on an analogy. Now, phase space of a system of particles is a collection of 6 numbers for every particle. They are the x position, the y position, and the z position, and the 3 momenta, the mass times the x velocity, mass times the y velocity, and I'm sorry, it would actually be the y speed, y is the direction, and mass times the z speed. So in order to do this, I chose a 6-sided die to be a individual particle, and each of the faces of the die represented one of the 6 elements of the phase space. And I chose 100, 1,000, a million, 100,000 6-sided die in there to model systems of particles. And as each atom is bouncing around, a die, that is, our atom is, a die is an analog to an atom bouncing around in a gas, was randomly chosen to be selected. So, and randomly means uniform probability. So each one of the possible particles could interact with another one. The actions were a mixture of random and deterministic, that is Newtonian. So what could happen in the die was that it could be rotated in the XY plane, the YZ plane, the XZ plane and the YZ plane. But one of those was chosen for each die. And then any one of three rotational angles, pi on 2, pi or 3 pi on 2, not 3, was chosen randomly and the rotation performed. So there was a mix of deterministic actions and uniformly probability choices among the actions. So this was mimicking what was initially called in most of statistical mechanics the postulate of equal probability something or other. Okay. So each die face, instead of being the usual 1 to 6, were either a 0 or a 1. 0 was assigned to the left part of a volume of gas, and the 1 was assigned to the right part of another volume of gas. Using it's not hard to realize that for n-dimensional real number systems, we usually live in R3, is actually equivalent to a line, R1. And there's a standard mapping for every element in R3 into R1. And of course, you can do it the reverse way. And that was the way in which I chose each of the positions on the left or right based on we had a tray of die, and its position would be mapped into each one of those locations. A 0 would mean to the left side and a 1 to the right side. Okay, so the average of the faces, the proportion on the left versus the proportion on the right, again, mistyped there, was computed for small equal time steps. The average, as expected, provided a rough equilibrium. That is, they started out all in one shape, one side, and then as they kept interacting with each other, they eventually stabilized at roughly a half, bouncing around it. So this is a analog that I thought might be easier to understand than entropy of how equilibrium works in a gas, how a system follows entropy increasing until equilibrium is attained. So I showed that independent of the number of die, from 1,000 to 100,000, the long-term behavior of the die were the same. The equilibrium and entropy increased until the equilibrium was the same. Considering the collection of particles that make up a system, by dealing with the whole collection, we call that, and the behavior of the system rather than the individual particles, is called coarse graining, one important concept in thermodynamics. In our simple model, the system was considered as the sum of the upward facing die making up our system. So this is our coarse graining, the sum over all the number of ones and zeros facing up. And rather than looking at the individual particle and what each one did individually, we could simply take a look at how the sum behaved over the evolution of that single number. So that's the advantage of dealing with coarse graining. You simplify a very complex system with a lot of individual interactions and locations and whatever, and we look at some coarse graining. So in a real coarse grain system, it is, of course, not a single number, but it's also very, very large. But although that number is very, very large, it's small in comparison to the collection of particle evolutions, the individual interactions. During the work that we had done, I've been using two types of system, mu-c and m-c, and I talked about ensembles, that is how you take a look at all of the actions that are going on. So the mu-c is the micro-canonical ensemble, and this is huge to the huge power collection of system evolutions. On the other hand, huge to the very large collection of coarse graining ensembles, which I called the macro-canonical ensemble. So finishing with our analyze equilibrium behavior, I described microstates, macrostates, phase space, and the relationship to microstates and macrostates, especially energy. The density of microstates, omega, in phase space, and here's the postulate I couldn't remember, the postulate equal a priori probability. The meaning of ensembles, time averages versus ensemble averages. And although if a certain property is considered to be true, then the two will give you the same. But generally, we just look at ensemble averages. Ergodicity, that's the property that the time averages and ensemble averages are the same. Equilibrium is basically that the probability distribution of microstates becomes unchanging over time. we looked at systems, real systems, where you can't isolate things. So we added a trick to thinking about our systems, and we separated our systems into a small system and a gigantic heat bath, so that the exchange would only be between heat, and the heat bath would be constant over time. So creating a a not quite isolated system, but a system that behaved similar to an isolated system. Not the same, but similar. The assumption of weakly coupled systems, the factorization of the density states, the independence of omega of macroscopic variables other than energy, the linearity of the log of the uh, density of states as a function of energy. And lastly, the definition of the state function for S or entropy using Boltzmann's result that it's Boltzmann's constant times the log of omega of E. Using that, we were able to define what temperature meant in terms of statistical mechanics. That is, there is a constant in the probabilities called beta, and beta is 1 over the Boltzmann constant times the temperature. It is the derivative of the energy in the entropy state function. And extending the entropy to include volume, because initially it was independent of volume. The definition of pressure was then also in terms of a derivative of the volume in the entropy state function. And we spent a fair amount of time in Maxwell's 1860 publication, which basically came the same result as Boltzmann's H theorem, the kT log of omega. And the reason that it was a little problematic was that there were two implicit assumptions in his paper, which he did not either define nor make a postulate or in any way recognize that they were needed. So some of his results were a little, although they got the same results, the assumptions weren't clear. But he essentially anticipated Boltzmann's entropy equation by 6 years on Boltzmann. So then we moved on to Maxwell's molecular speed probability distribution, or kinetic energy, the Maxwell distribution. And this is, of course, the molecular speeds are not uniform. And we talked about how Joshua Gibbs' definition of entropy allowed unequal probabilities and is identical except for a constant to Shannon's information entropy, the Hartley entropy, as opposed to the Boltzmann entropy, which is just a constant between the two. And so H is the sum from I equals 1 to n of p sub I log, well, there should be, there is the constant is slightly different because Shannon did it in log base 2, and of course Gibbs did it in log base E. In entropy, they add these funny units, although everything, of course, in terms of the underlying information entropy, is unitless. But if it's called log 2, it's called bits. If it's log 3, it's nits. If it's log E, it's nats for naturals, etc. And I forget what the base 10 is, but there's all these names, and the only reason for using those units is to let you know which base of the logarithm is used in these calculations. Lastly, we moved on to how Louisville's theorem showed that the probability density of a system in phase space is conserved in time. And we're going to come back to this because it is an example of Hamiltonian flow. So this is we're going to use the same example again when we get to Hamiltonian flow. So I finally moved on to information theory, and we began to understand Claude Shannon's 1948 groundbreaking Bell System technical journal entitled Information Theory. Shannon had a real gift, a genius for abstraction, and he determined what information is not. He didn't talk about what it is so much as what it is not. And he realized that the mathematical idea of information is not isomorphic to meaning. So meaning is independent and something which an observer uses information and creates meaning from the information. See, he focused on what is communication, how does it work, and what is information. And Shannon showed two different versions of this. First, the simple one, information is the distinction between different messages. So there is some way to measure a distinction between any two different messages. And there's lots of possibilities. A communicated message is one of many different possible messages. So we usually talk about either an alphabet if we're talking about individual symbols, collections of words if we're talking about, but anyway, there's some kind of communicated message that is based on a primary set of the individual units of the message. So we discussed the 5-bit Bateau code. This is the one that is used by the blind. The 7-bit ASCII 7-bit code. And I showed how fixed alphabet lengths would determine the number of bits for coding an alphabet. Both Shannon and John von Neumann were at the Princeton Institute of Advanced Studies during World War II. Johnny thought about how self-reproducing machines could be built. And it was his incredible insight that you didn't have to have a miniature copy of the object in the object that you're trying to describe. So if you think about a Julia set, if you keep going down finer and finer detail, you keep seeing the same Julia set reproduced and reproduced as you go down to smaller and smaller sizes. And this would give you an infinite amount of information that you'd have to be able to describe. So Johnny's insight was that you didn't need to have the object contained in a miniature copy, but simply a list of instructions to build a copy. And of course, this is very similar to the way biology came upon it in evolution, that is using DNA, which is a list of instructions telling you how to build various proteins. So one of the fascinating connections between information science and physics, physicists have shown that information plays a fundamental role in the basic laws of matter and energy. Why do we say that? Well, a partial answer is just to think in a general way about the nature of events, that is, cause and effect. Suppose we communicate a message sent and received through some medium of a transmitted signal, and every sort of physical cause and effect link. This process can be regarded as a kind of information. So if you've got two protons at high energy crashing into each other, we know that there's going to be a bunch of particles coming out.
We've lost your audio.
Yeah, somebody muted me remotely. Bob, stop that. Somebody muted me from out there. I assume it was you, Bob. Anyway, so if you have an interaction between the two particles when they collide, that is a two messages going through a channel, the interaction, and the cause and effect that we're talking about here, where the particle results, the junk that comes out of the interaction, those are usually all kinds of particles that have a short time over which they disintegrate. So all of those various steps in the physical cause are changes in the information. And eventually you get to a stable particle, usually photons, but could be other things, electrons or muons or something. Well, muons decay, so the lowest mass level, lowest mass shell level. Anyway, um, this kind of a process can be thought of as a kind of communication of information over time and space. And this is what information theory is all about.
Good. Okay, you wanted a question? Could you go back to the previous slide? Uh, how does time fit into this? In when you're all of the descriptions of communication and information transfer. Communication is moving information from the sender to the receiver.
Right, and that's
Okay.
of course over time.
That's over time, and so in the and it is the information that's sent and received. There was a lot of discussion about what affects that and its validity and things like that. It is the information is I'm trying to relate sent, received to cause and effect and time.
Well, every channel over which messages are transmitted are physical systems, and every physical system is based on cause and effect. So whether you're talking about a wire, a electrical, a radio wave, whatever it is, all of that is cause and effect.
Now, I guess I can relate the physics part of it. I'm okay. This seems to be obviously what a lot of everything you've done for the last 12 lessons is trying to draw this connection.
Yes.
And
absolutely.
That's why there's so much to digest there. And your analogy with the subatomic particle interaction, is the message the states?
Yes, well, I probably shouldn't have talked about because this is quantum information as opposed to traditional Shannon information. I should have talked about some two billiard balls bouncing off each other. Those are much more close to what we deal with in Shannon information. And it gets confusing in quantum information. So I've been trying all as we go along to avoid quantum things, because you don't have a state the way you do in a Newtonian system.
Okay.
You've got a function space, the wave function, and that is, doesn't result in specific message transmissions, but probabilities of possible things happening, etc. So it's much more complicated, and I shouldn't have used that as an example. I apologize. That was a mistake on my part.
Oh no! I think that's what to make this transition. We have to try to think through some of these things. Are they related in the mathematics only, or is there more to it than that?
Well, many physicists actually think there's a lot more to it, and John Wheeler, tremendous, wonderful person who created these sets of words that communicate so much, like black holes, and many other things that he created. One in particular was it from bit. And he thought that, you know, when you start with a bit of information, you're actually talking about a physical uh, event of some kind, and that information is the has the is the underlining uh, constituent of the physical object. So everything in the standard model of physics is about excitations in fields. And so all of those fields, uh, you know, the interaction, the rubbing between the two fields um, will create
Okay, I
various
lost you again.
kinds of particles. Sorry?
I'm sorry. There, you just muted for a second. I don't know. I don't hope I didn't do that. I just.
No, I just got a message that said the internet is unstable. Sorry. Okay. So the idea that Wheeler had was that you start with the information of what causes the friction between the fields in the standard model. And every time you have a certain creation of a bit of information in the interaction between the fields, the result is a creation of an excitation in the field that is what we call a particle. So from bit to it is the idea that or it from bit is the way he actually said it. I apologize. Um, the it from bit is the idea that the bit is more fundamental than the interaction result, the excitation in the field.
Okay. All right. Thank you. I mean, obviously, it's just it's fundamental to what you're trying to kind of convey and communicate to others. But that makes a little bit of sense. I mean, enough that you can grasp in on the context of what we're doing. So, thank you.
Okay.
I wanted to just put out my thoughts here. When you're talking about a cause and effect, you're talking about, I just kind of made this up, a pusher and a pushee. Something is pushing on something else or interacting on something else. So you have to have A interacts on to B. But okay, my thought is I'm looking at, okay, what is interacting on A to cause it to interact on B? And it seems to me that for every cause, each cause must have something causing it, interacting on it. And
Yeah,
what that depends on.
When you look at it in terms of special relativity, you're at a location where an event is occurring. When you go backwards in the light cone, you see everything that ever caused to create the interaction that's currently happening. So you can track backwards over time to everything that ever happened before that wound up as this interaction. So this is how the pushy came to be. And
we've lost you.
Okay.
Oh, you're back.
Okay. Sorry. So when you look backward over the light cone, you find all of the things that happened over the past infinite amount of time that created the pushee to be in the position to do what it's doing to the what did you call the other one? You push and you
pusher and pushee.
Okay, so the push or I'm sorry, the push or you look backward through the light cone and find everything that created it to become where it was at the current moment time. And the push E, the one in, no, the push E is the one that pushes the pusher?
No, the pushy is being pushed.
Okay. So the push E, that's the way I thought it was. So the pusher, you look backward in the light cone, and after the event, at the point where they're at the same point in space and time, then you look forward in the light cone to see everything, those two particles, the push E and the particle and the push E and the pusher, both go forward in time and create a bunch more of cause and effect.
So every pushy turns into a pusher. It
right.
pushes on something else. So the beginning of the light cone, I guess, is the Big Bang. Is that right?
Yeah. Yeah.
Okay. So what this means is that the whole universe, there always has to be something in motion. Nothing can, if the entire universe came to, you know, a standstill, reverted to entropy, there would be nothing to push on anything else. So you always have to have something pushing on something else.
Yeah, the vacuum, one of the things that's the interesting result of quantum field theory is that the vacuum is not empty. So all of the fields, the 26 or whatever number of fields there are, uh, the various quark fields, the gluon fields, the electron, all of those things exist, and they always have existed and always will exist. But they are not, even in the vacuum, they're not at zero energy. They're at a lowest energy state. It's very small, but it is non-zero. And because of the uncertainty principle, that means that the field will produce very short amounts of time during which various antiparticles will be created. And so even in the vacuum, with nothing else in the universe, just the vacuum, you're always going to have these creations happening around you. And it is that idea which is actually the basis of Hawking radiation. But that's not for the vacuum. That's for the vacuum around a massive object. So that's slightly different. But the idea that the vacuum, with absolutely nothing in the universe, will still produce particles of various kinds over time. So there is nothing that is ever still, even in the vacuum.
Thank you.
You're welcome. Okay. So in the 20th century, the physicists regarded nature as a complex interplay of forces or energy transformations. In the 21st century, physicists have sort of switched and regard nature as a complex network of information. And our understanding of physics influences the concepts of information, just as the concept of information influences physics. Again, John Wheeler, great slogan maker of physics, said the idea in a pithy slogan, "It from bit." It might be that everything in the universe, every it, actually emerges from an underlying information process. So there are three heuristics that are about physical information. One is the idea that information is always physical. And this was postulated by Landauer. Information is always associated with the state of a system. Information is relational. Information refers to the relations among subsystems of a composite physical system. So if you think about, we've been talking about communication channels. So every, you've got a collection of messages. Those are translated into codes that are become a transmitter. The transmitter is a physical representation of the code that you've set up. That's some kind of physical system. And it then transmits over a channel, could be a wire, could be a radio waves, it could be a whole bunch of things. But each one of those transmission systems are physical systems, and they use cause and effect. So eventually they get to a receiver, because things happen at the speed of light at most. And if you're in wires, it's actually only about 2/3 the speed of light. But the relationships of the composite system are from the transmitter through the channel to the receiver. There is additional meaning that is translated from usually biological systems to create the symbols to be sent to the receiver. And an observer at the receiver sees those symbols and translates those into meaning. But the information has nothing to do with the meaning. Those are stories made up by biological systems. Okay, so lastly, information is fungible. And Bennett stated, information can be transformed from one representation to another. So the information is a property that's invariant under such transformations. So think about, again, our collection of, and we'll use alphabets in this particular case. So think about the collection of alphabet. Those symbols are defined as codes. So you translate the symbols to various codes. And we've talked about various kinds of codes, and there may be various amounts of inefficiencies in that transformation. So you know that, for example, with 26 characters, you know that 2 to the 5th is 32, so 5 bits would be enough to create a code that was distinct for every symbol. But 32 is larger than 26, so there's some excess. So if you think about those fixed size bits being sent along a channel, you could use a Huffman code to make it a variable length code. And the variable length code would be shorter than the fixed length code. And then you block those together into a fixed number of bits, and those get accepted at the other end. If there were no distortion, no noise, you'd be able to decompose it because that's an instantaneously decodable system. If there were noise, we could change the design of the bits that we had shrunk to make them longer. And the Hamming distance and Hamming codes are ways that do that. So you can, depending upon the design of the code and the number of bits you're willing to accept in terms of inefficiency, you can have 1, 2, 3, n bits of error distinguished and corrected. So there's all these trade-offs in the information given in the original symbols and transformed from these various representations. And at the other end, their inverse is used to decode the information. So the information that you're trying to communicate is the collection of symbols. And that is a property that you want to keep invariant over all of those transformations. So information can always be transformed from one representation to another, and the information itself is the property that's invariant under such transformations. So physical, relational, and fungible. Okay, so suppose somebody sends you a 1-bit message. What does it mean to receive half of the message? That might seem silly. I mean, it might seem strange. A 1-bit message is a single atom of information, or a 1 or a 0, a yes or a no. It is simply one of those two people. So let's remember our people, Alice and Bob. Alice has been asked a question by Bob, a yes-no question. And Bob is waiting for her answer. Possible answers are equally likely, 0.5 yes and 0.5 no. Now, obviously, Alice's probabilities are considerably different, or he wouldn't ask her for the question. But he's ignorant, and he trusts her to have the proper answer, so he asks her for her answer. And the entropy of the message, because it's taken from the point of view of Bob's probabilities, is 1 bit. Alice had better have nearly 0, very small entropy, or she wouldn't be able to answer the question accurately. So Bob lacks that amount of information before Alice speaks. So how much entropy will he gain when he hears accurately her answer? However, Alice and Bob are standing in the midst of a noisy party. So this is going to be a problem. After Alice gives her answer, Bob is not entirely sure he hears it correctly. He thinks she said yes, probably said yes, but he isn't quite certain. So Bob updates using Bayes' theorem from his prior probability of 0.5, 0.5, and based on the the structure of the conditional probabilities that he has, he determines his posterior probability is 90% certain. So Bob still has some entropy even after Alice speaks. So her message for Bob still has uncertainty. Bob has the uncertainty about her question. So all of this entropy is about Bob and his probability. Applying the Shannon entropy formula, the entropy remaining is the average surprise. So Bob started out lacking one bit of information, and now afterwards he has 0.9 log base 2, 1 over 0.9 plus 0.1 log base 2, 1 over 0.1, which winds up to about almost 0.5 of a bit. So he had one bit of uncertainty. After he received the message, he only has a half a bit. So the atom that we're talking about here, because it's based on the probabilities and how those are updated, may not be, if there is noise, if there is distortion, the ability to distinguish reliably between possible alternatives. Bob has gained some information, but he can't do it with perfect reliability. So he went from one bit to a half bit. So communication theory, we've been talking about it without really thinking about how it works, but we have some referent V. So we have some collection of messages. These are created in a signal. That signal has distortion, has noise, that eventually comes to a receiver, and at the receiver there's signal processing and digitization. And then we do error correction and decode it, and we wind up with our resulting copy of B, possibly, depending upon how much error correction is enabled and how much signal distortion and noise in the environment is. It may be, an accurate decoding, or it might be not accurate. But the key point is all of this stuff happens to the signal, not to the referent and not to the decoded result. So there's no communication channel that's totally immune from error. So how do we take noise and error into account? Shannon introduced the concept of a communication channel, which we've been talking about, and this refers to any physical process to convey information. So if the output were exactly the same as the input, then the idea of a channel would be a trivial one. But the channel determines which outputs are possible, and they're all dependent on the likelihood of the output given various inputs. So we need to describe the rule by which the input leads to the outputs. And these rules are all specified by conditional probabilities. And in his 1948 paper, the fundamental problem of communication is that of reproducing at one point either exactly or approximately a message selected at another point. That's what we've been talking about. Frequently, the messages have meaning. That is, they refer to or correlated among, according to some system, with certain physical or conceptual entity. These semantic aspects of communication are irrelevant to the engineering process. So that was one of the insights that I spoke of earlier, namely that the meaning of these messages is irrelevant or orthogonal or just not relevant to the physical aspects of communication. The significant aspect is that the actual message is one selected from a set of possible messages. So you have a collection of symbols, you can put them together into what are possible messages, and then of course, if they're words like English, most of the large collection of possible words in the English language are actually useless to understand, and they're not part of the collection of possible messages. So the system that we put together has to be designed to operate for each possible selection, not just the one which will actually be chosen. Because when you're designing a communication channel, which of the actual messages will be sent is unknown. So you have to design the channel in the face of no knowledge about what the message is that's going to be sent. So the communication system is using, this is figure 2 of, or one of the figures, this is figure 2 in this one, but it's a figure from Shannon's paper. So you have the information source, and then you have a message. So you can think of the information source as a collection of all possible messages without any understanding of what the meaning is. You take one of those, put it into a transmitter, which converts the symbols on the message into some kind of a signal that can be sent over over this channel. The signal will, of course, also have noise and distortion. And so the received signal will not be identical to the sent signal. The receiver, a device at the other end, is used to decode the signal sent by the transmitter. And if it's all well designed, the received message will be very close, if not identical, to the sent message, and the observer at the other end is the destination from the receiver. So this is the way a communication system works. So an information source produces a message or a sequence of messages to be communicated to the receiving terminal. The transmitter operates on the message in some way to produce a signal suitable for transmission over the channel. The channel is merely the medium used to transmit the signal from the transmitter to the receiver. And that is because we have to use causality. So the receiver ordinarily performs the inverse operation of that, the transmitter reconstructing the message from the signal. And the destination is the person or thing for whom the message is intended. So these ideas are the basis for Shannon's primary information tool, the entropy, which we recognized was identical to the Gibbs entropy modulo a constant and the base of the logarithms. Communication channels, we talked about it in the past, the symmetric channel with error and the binary erasure channel. Mutual information describes the relationship between the terminals and the transmitting terminal and the output terminal. The importance in redundant symbols to reduce the error rate is important. The channel capacity, which was defined in Shannon's paper, limits the transmission rate. We talked about the Kullback-Leibler distance in its use for correcting errors in transmission. Now, one of the things that we had to deal with was the fact that although it's called a distance, in geometry it's not. So it's a pseudo distance, but it can still be used in correcting errors in transmission. So knowing that, as long as you don't exceed the channel capacity, the maximum amount of information that can be transmitted per second, there exists a coding that you may both compress and error correct messages to any degree desired. And of course, anytime you add more and more error correcting, you slow the rate at which the material can be sent. There's a limit to the amount of compression that can be done, but the error correcting, that as you do more and more error correcting, you're going to slow the transmission down. So we talked about various ideas of implementing these ideas. One was the Morse code. One is the ASCII 7-bit code. We talked in general about fixed and variable codes. We talked about coding functions for channel input, morphisms and their decode ability. They're actually one-to-one. Prefix-free variable codes or instantaneously decodable. So you can have variable codes, and by designing your codes very carefully and having this property prefix free, then you will be able to, assuming accuracy and no distortion, no noise, you can immediately decode all of the prefix-free variable code, which means you've done compression. And we talked in particular to the Huffman codes, which was an interesting idea. I mean, it was a question to write an essay in his graduate school course, and Huffman, rather than writing an essay, just said, "Oh, here's the result." He found the theorem for how to create a Huffman code that would be variable, reduce the number of bits, and make it instantaneously decodable, assuming no noise and no error. So they're useful because they allowed us to optimally use inefficient coding schemes and variable length codes and efficiently. So, however, as I've mentioned several times, he assumed there's no noise or distortion in our channel. There is, of course, no such channel. We know that there's two additional features that we have to look for in our coding and decoding schemes. That is, being able to diagnose errors that arrived at the receiver. So the receiver must be able to recognize that there was a number of bits that were sent and during any particular code that was received. So we must also be able to correct some acceptable number of bits that were diagnosed but in an erroneous message. So, and we started to talk about last week about Hamming codes, and Hamming distance and Hamming codes are the primary stuff that we're going to move on to. Okay, so the summary is that transmitting messages is an important practical problem. We have demonstrated that Shannon was able to measure the amount of information along communication channel. Coding theory includes study of compression codes, which can send messages more cheaply, and error correcting codes, which ensures that messages remain legible even in the presence of errors. Cryptography, on the other hand, makes sure that messages remain unreadable except for the intended receipt. And we'll eventually get to show that these things actually have much in common. So
I wanted to ask you something. I think I may be jumping the gun because you're going on to error correction, but since this transmission and coding deals with probability, there's always, at least up until you're going to tell us in error correction how it's perfect, but there always exists some probability that the receipt of the transmission is interpreted incorrectly.
Correct.
And of course, you know, we can envision some scenarios where even the smallest error can be very grave in consequences. So I mean, all right, you're going to tell us about error correction. The only thing I can think of is that they go back and forth a few times going, is this what you meant? And is that what you meant? And until, you know, they get it, you know, pretty close to what the original intention was. I remember there was a movie several years ago. I think it was a foreign film from Mexico or something like that called The Stallion. And it had to do with an incorrect receipt of transmitted information. Transmitted information could have simply been by verbally, but it was the difference between a horse in general, the generic horse, versus a male horse, a stallion. And that made a big difference, and people got killed because of it and all of this kind of stuff.
Well, there's two aspects of this. The first is the remember, information is independent, is orthogonal to meaning. So if somebody sends a symbol that is a horse as opposed to the symbol for stallion, that has to do with meaning. The error correcting has the process of making sure that if it's a horse that's sent, then a horse is what's received. Or if a stallion is sent, then a stallion is received. But the meaning of the message is not known to the communication system, the channel. The system for decoding, moving from point A to point B, receiving and decoding is whatever the symbol set that was sent, we want to accurately receive it. But if the message was incorrectly sent, not the message that you want, that's part of meaning, and that has nothing to do with information. Do you understand the distinction?
Yeah, yes, I do. Yes.
Okay, so
You're talking about interpretation of what you're looking at.
right, and that is not part of information. So it sounds to me like, I mean, I don't know the movie, so I can't say with complete accuracy, but if they sent the wrong word, then that's not part of decoding. That's not part of information theory. That's part of meaning and has nothing to do with information theory.
Mm-hmm.
Okay.
If we're going to connect eventually this idea of information flow with cause and effect and physical systems, don't we at some point have to worry about the meaning of the message, so that when we are transmitting the idea of a force, if it's a big force or a little force, force changes, that has to somehow be not just communicated, but there also has to be the meaning involved with it. Is that where we're headed? I guess I'm not completely sure.
No, we're actually not. The idea in physics is that the physical laws don't have meaning. So they're simply descriptions of how things interact, how cause and effect occurs. And you can, the only meaning that we have, excuse me, The only meaning that we have is the repeated experiments that demonstrate that our laws are accurate, that every result that we produce in our laws is actually demonstrated to be accurate in experimental result. But there's no meaning in physics.
Bob?
Yeah?
That earlier when you were, and I think this makes a lot of sense, and this today's discussion, I think, is really helping tie a lot of this together. I was thinking if there was some mega meteorite that tomorrow struck the earth and vaporized everything, we were all gone. The next day, the world would just continue. the universe would continue to operate as it's always operated. And because all the interactions, all the information, if you want to present it in under that context, all the information that exists and is transmitted between everything that exists in the universe would continue, but there would be no one to interpret that as we try to do. So it is the human part, that meaning that has just been brought into these last couple questions, that we only, it's just us that sees meaning.
Right. It's part of, I mean, this is not something that is, well demonstrated, nor is it well accepted in biology. But my feeling is that the way that the brain evolved was because if you could guess ahead what was going to happen, if you could make decisions to avoid bad outcomes and choose decisions for ones that would improve our ability to reproduce, then we built this machine called the brain, which basically looks at the inputs and creates all of these approximations for how we could see what's happening. When you play baseball and somebody hits a ball, you start running. You almost instantly know whether it's going to be towards you or it's going to be behind you. So you have to, you almost immediately turn around and go if you know it's going to go the other way, or you head in if it's going to be short. And these things are all part of the brain that were developed to increase our ability to be able to reproduce. Now, eventually, we created this system, which we call logic and set theory and mathematics and physics and a whole bunch of other things that were ways for us to be able to understand without having a lot of experience. That was all of our original brain was designed for creating reactions, in our bodies to save us. But eventually some part of the brain figured out, oh, we can actually take a set of systems to put together and follow their conclusions and find out whether or not, the implicit results are accurate. And if they are, we begin to call that a science. And it changed the nature of our culture, of our ability to survive, to the point of where, when we were pretty much instinctual 100,000 years ago, we were very very small number of mammals, less than 1 million, and then today we have, you know, something like 8 or 9 billion people on the planet. So the ability of the brain to figure out how to survive has been the most amazing creation of evolution ever. And you know, the idea that there were mathematics that we could take a look at the in the inferences, or you know, take a look at the result and calculate what was going to happen with it, is the basis of almost everything that we now operate on, whether they're transportation, or communication, you know, entertainment. Everything that we do now is based on those recognitions that there is this science that we can create that allows us to understand what the future is going to be like. And furthermore, we can do it in a controlled way, a laboratory function, and without having to, you know, have a lot of people die in the process of learning. So, yeah, I think that the brain is an amazing machine, but you're right. If we were to have a, you know, an immense collision with an asteroid that wiped out the people on the face of the planet, the planet would continue to operate totally fine. It, you know, if there were any other animals that managed to escape that, eventually something else would come up. So
yeah, no, yeah, actually, this is really interesting. And that I did spend a fair amount of time working with artificial neural systems. And then in doing that, I read a book which was all about how the brain builds mental models of the world, and then how people operate under those mental models. And I'll dig up this reference because it was a paperback written about 20 years ago, which I thought was quite insightful. But I guess the reason I brought up that example was the application to thermodynamics and to the way in which physical systems interact and develop, and the world just goes from this instant to the next instant. What we can do is describe it a variety of different ways. And the evolution from the way in which physics and science was looked at in the 20th century versus when you talked about the 21st century, the ability to make sense out of it, how to improve our model, both our mental model, but then also the mathematical model of the universe based on information theory, is really insightful. And I really appreciate you dragging us all along on this path, because this is really quite interesting.
well, thank you. I find it really, really interesting. So, you know, it's going to take a few more lectures, but we'll get there.
Well, I'll dig up this reference. It's hidden in my stack of the few books I brought after I retired, but it was one of the most insightful books I read. And it's about how human neural systems build these mental models. And I think the example you gave of just trying to catch a ball, I mean, how do we do that? How did the brain get to the point where it could do that? And then what does it actually do at the physics level with the neurons, with the chemistry, with the physics that goes on in the brain? And it's very readable, and maybe some others would find it equally as informative, but it did open up how we build these mental models. And that's how we respond. And the irony of it is, and you see this every day now, everybody builds a different mental model. They're not the same mental model. Your equation is one that at least a bunch of people may accept, but in terms of the behavior of so many other of the systems in the world, we all have built these different mental models.
Oh yeah, yeah. No, that I absolutely agree, and I would really look forward to reading that book. So if you could send it out, I'd appreciate it.
Yeah, it was written by the guy who eventually whose company developed the Palm Pilot, and he started as a graduate student at Berkeley. And
Huh.
I should know his name, but for me, names and that kind of data just goes right in one and out the other. But I'll send it out to everybody.
Yeah, I knew his name at one point in time too, but I don't remember it either. Anyway, yeah, no, I didn't realize there was actually I mean, this is just all ideas that I've worked on in my head as I've gone along reading, but I'm glad that there's somebody who's, followed it up, and that it actually can be more formal than what I've simply, loosely connected with.
Well, what you said was pretty consistent with what I've read. And I mean, I spent a lot of time trying to figure out how to get into other people's brains, those students, and to make them think differently. And that's what, and then actually working with these artificial neural networks, there's a lot of interesting science and expertise out there in this domain.
Yeah, the problem right now is that people are finding that the AI systems actually don't work the way our brain does. All of these systems that can identify cats from dogs, from bears, from whatever,
Book by Jeff Hawkins.
we as people almost always identify based on shapes, by looking at the outlines of objects that are going on there. However, they found just within the last 5 years or so that all of the AI systems that are so successful actually are based on texture. So you can distort images that were used to create the AI, and by blurring them in a certain way so that it messes up the texture but keeps the shape identical, they find that the AI system just completely breaks down, doesn't understand what it's looking at, and a person, of course, because the shape is the same, they know it immediately. So they found that a lot of these AI systems are not based, are not built in the same way as the human brain, and that's one of the new, really interesting discoveries. So
I don't want to get off, because I mean what you've done here, but I'm actually working with some face recognition software right now for a museum exhibit that I'm helping develop. And it does some of the weirdest things you can possibly imagine. It's really quite, and so I keep thinking, boy, I sure hope this isn't going to drive my car one of these days. This is what I really don't need. So I'm sorry, I'm taking you off in a wrong direction, but I will dig up that book and share it with you.
I think I found
Thank
the
you.
book. I think I found the book. Is the guy's name Jeff Hawkins?
No, I don't think so. I'm going to go get it out of my, I'll go
Okay.
grab it. It's a blue paperback.
There's a book. He's listed as the main founder of
what's it called?
Pilot.
What's the title of the book?
On Intelligence.
I think that may be it.
On Intelligence by Jeff Hawkins. And yes, it is blue.
Yeah.
okay, let me write that down. Okay, so come on, get my pencil out. Send it out, please. Okay. Anyway, originally code was a device for making messages hard to read. This was cryptography, and we're going to talk about this later. Obviously, right now, we're getting very close to the end of our lecture, so I may cut this short in a fair amount of time. And come back, I may just come back to this next week. I hope the review wasn't a waste of time. I found it interesting to just put it together. But I hope everybody found the review that we've been doing so far a little bit of insight into how all these things connect together and why they're important. So with that, I'll just ask questions.
Bob, could you send out the review in sort of a preliminary, say preliminary
No questions?
video? I just have a question. My question is, if I would like to see this review again, instead of waiting for the lectures to get corrected. So that's just a request.
Okay.
And Gail was correct. It is On Intelligence by Jeff Hawkins. And it's, I will send out the US ISBN number, and it's probably still available. But yeah, I think the review helped from the point of view of it did help tie this together, kind of where you've been, where you're going, and then, so that was very beneficial.
Great. All right. Well, thank you, everybody. I'm about to, let's see, I'm going to stop the recording.